The last topic in our course is going to be what's called phase plane analysis. I want to point something out, which is that so far when we've referred to solving a differential equation, what we meant is to provide an explicit solution to solve it analytically, meaning I give you a differential equation or a system of differential equations, and we find an explicit function of t, like e to the lambda t times cosine a t times some particular eigenvector or whatever. Sometimes though, when you're applying differential equations, having a formula for it isn't really the point of finding a solution. What we really care about is what the end behavior is, what happens to the solutions over time. If you recall, there have been several questions we've encountered about an oscillator, what happens at infinite time? What conditions can we put on the coefficients of the oscillator to make sure that it doesn't have resonance? Questions like that. That's what we're going to do, and we're going to come up with a sort of coordinated scheme for doing this. I want to introduce this in the context of a particular problem where what we really care about is the end behavior of the system, what's going to happen in the long run as t gets close to infinity. Let's say we're population biologists, and we'd like to understand a system that consists of lions and zebra. So we'll write the population of zebra at time t as z of t, population of lions at time t as L of t. What we'd like to do is take our biological principles, what we know in general about how lions and zebra interact, and we're going to encode them as a differential equation. I'm going to make a few assumptions about this that will help us write that differential equation down. The first two assumptions I want to make are about how lions and zebras are in the absence of the other species. So if you imagine a zebra population where there's no lions, maybe lions are the only predators for the zebra, so the zebra will, if grass is plentiful enough, etc., reproduce at a reasonable rate, let's say 5% per year. So every season, you take the current zebra population, multiply it by 0.05, that's the number of babies that are born in that year. Lions, on the other hand, need the zebra. The lions primarily rely on zebra for food, so the lions are going to start to die off at a pretty impressive rate, so 10% per year. That sounds like a really fast population decline, but hey, if your principal food source is gone, what are you going to do? Now we're going to make some assumptions about how the species impact each other. We're going to assume that each lion eats 3 zebra per year. So if I have a very large lion population, that's a lot of zebras being eaten per year. I'm going to assume that the effect of eating zebra on the lions is to give them extra resources, enough so that each zebra will produce 2 additional lion cubs that year. So I'm just picking these numbers, but if you're a biologist, or if you know a biologist, you could ask them these numbers. The point is these numbers, 5%, 10%, 3, and 2, those are biological facts. A biologist could go out and observe zebras and lions interacting for a short period of time and understand how to derive these numbers. What I'm going to do now is take those numbers and put them into a differential equation. So I'm going to think about the effect on the rate of change of the zebra population that the zebras have and that the lions have. The zebra reproduce on their own at 5% per year. That means each year you expect to have 0.05 times the current zebra population. Now, on the other hand, lions are eating the zebras, and for each lion you have 3 zebra that die that year. So there's our equation for dz dt. The same thing for the lions. So the effect of the zebra population on the lions is to increase the lion population. Each zebra produces 2 additional lion cubs in that year. On the other hand, if there were no zebras, you see that we would decrease the lion population at a rate of 10% per year. So for each of these species, you see the zebra population tends to help that species. The lion population tends to hurt that species. That's true for both zebras and lions. I want to write that as a vector differential equation. Okay, there we go. So if you're a population biologist, and you really care about what happens to the zebras and the lions, what could we do? We could solve this explicitly, find a formula for z of t and L of t. We have all the techniques that we need to do that. And then ask, okay, what happens as t goes to infinity? Compute a limit as t goes to infinity. That's one way to do this. Let's actually try to carry that approach out right now. This is a constant coefficient system, so we need to compute the eigenvalues, eigenvectors, compute a matrix exponential maybe. So there's the characteristic polynomial, and we can of course find the roots of that using the quadratic formula. You can see that the number under the radical is going to be negative. That means our eigenvalues will be complex. I've computed the real part. The imaginary part is the square root. It doesn't really help to write it out, so I'll just call it alpha for the moment. Okay, how do we proceed from there? We need to find the corresponding eigenvectors. They're going to be complex. Oh gosh, it's just a major headache, right? To do this explicitly. Kind of a pain. It's the kind of pain that maybe you expect in a math class where the point is to learn how to solve these things. But hey, we did that already. Let's move on. So what I want to do here is just ask, looking at the coefficient matrix, can I sort coefficient matrices into different categories where the end behavior, or what the solutions look like, are sort of common. So let's do that. I'm going to do this just for 2x2 systems with constant coefficients and homogeneous. So I'm not considering that B term at all. So what is the characteristic polynomial of this general matrix? It's easy to work out. And then I want to take a look at this, and I realize that the coefficient of lambda is minus trace of the matrix, and the constant term is the determinant of A. We can easily compute the eigenvalues using the quadratic formula, and you see that the important question is that number under the root, is it positive, negative, or 0? That'll tell us something about our eigenvalues. By paying attention to whether the square of the trace is greater than, less than, or equal to 4 times the determinant of the matrix, you can sort out what kind of eigenvalues you have. So either 2 real, 1 real, or 2 complex. They have to be complex conjugates. If the trace of A happens to be 0, then you get a purely imaginary result. So what we're going to do is sort our behavior according to those. And I'm just going to give you a list of what the behaviors look like. We're going to involve a lot of exponentials, some sines and some cosines. Here's what it's going to look like at the end of the day. If you have all real eigenvalues, and let's say that they're distinct. So you've got lambda 1 and lambda 2, they're not the same number. We're also going to assume that neither one of them is 0. Then there's 3 things that can happen. Either they're both negative, they're both positive, or one is negative and one is positive. Let's try to understand what the behavior is for each system like that. I'll do the one for both negative, and then I'll just draw the pictures for the others. So if lambda 1 and lambda 2 are both negative, because these are 2 distinct real eigenvalues, each one has a corresponding eigenvector, which I've sketched, and let's see what's going to happen. If your initial value is on this line, the line spanned by v1, well, what's going to happen? That means that c2 is 0. We only see c1 e to the lambda 1t v1. Lambda 1 is negative, so that's going to force us to come in toward the origin. The thing is getting smaller. So that's what happens if you start on this line. Actually, that happens on the entire line, so if we start over here, opposite v1, we're still going to come in. That's what happens if we trace x of t, thought of as a parametric curve. If it starts along the line spanned by v1, it stays along that line, coming in toward the origin. What about starting along v2? Well, lambda 2 is also negative, so again, we'll come in along that. Now, what happens if we start someplace else? Then c1 and c2 are both going to be non-zero, which means we're sort of taking a little bit of v1, a little bit of v2, and we're adding them together. Let's see what happens. And the shape is going to look something like this. So if we start over here, as we come into the origin, we're bending more and more in the v2 direction. Why is that? Well, look at these 2 coefficients, e to the lambda 1t and e to the lambda 2t. Lambda 1 has bigger absolute value. It's negative, so e to the lambda 1t is much smaller than e to the lambda 2t, which means that in this average between v1 and v2, v2 is going to be much more present. So as t goes to infinity, we're coming toward the origin, and we're looking more and more like v2. As we let t go to minus infinity, that is to say we think about starting further and further back, well, we're looking more and more like v1. Lambda 1 times a really big negative number is a very big positive number, much bigger than e to the lambda 2t, so v1 dominates, and our curve is looking more and more parallel to v1. Let's do the situation where they're both positive, and in that case, it looks the same way, but lambda 1 and lambda 2 are positive, so instead of things getting smaller, they're getting bigger. The only difference between these 2 cases is which way the arrows go. Now let's take a look if one eigenvalue is negative and one is positive. What happens there? Well, if v2 corresponds to lambda 2, we're going to move out from the origin along that line, and we're going to move into the origin along v1. What happens if you start with other initial values, things that aren't on v1 or v2? Then you're going to look like a hyperbola. Okay, so that's the case of 2 distinct real eigenvalues, neither of which is 0. What if we have multiplicity 2? If the 2 eigenvalues are equal, that is to say they have algebraic multiplicity 2, and the matrix is non-defective, then there's 2 possibilities. Either that eigenvalue is positive or it's negative. In either case, after you diagonalize, the diagonal form of your matrix will look like a multiple of the identity. And we know how to compute the matrix exponential of a multiple of the identity. It's just e to that multiple times the identity. So our solutions will look like you pick an initial vector, x, and then you scale it. If the exponential rate is negative, then you're scaling it down. If the exponential rate is positive, you're scaling it up. So what do our trajectories look like? What do our solutions look like? There are still several cases we haven't considered. One of them is if one of the eigenvalues is 0 and the other one isn't. So what does it mean for an eigenvalue to be 0? It means that A kills everything in that direction. Since we're solving a differential equation, that means the right-hand side is 0, which means things just stay constant along that line. That is to say, if you start anywhere along this line, your value will be the same. You just won't move. it just sits there. There's a solution, it just sits there, etc. Lambda 2 is positive. That means we're going to tend to move out. If we're along V2, we're going to move directly out along that line V2. And what happens in between? We're going to move out parallel to V2 away from V1. And then if the non-zero eigenvalue is negative, it'll be the same, but with the arrows reversed.